hence the term easy melting. Now, all alloys, irrespective of their analysis or analytical composition, exhibit across their entire analysis a constant freezing finish temperature, which is when they will be all solid. We term this constant freezing temperature line the eutectic temperature line. In all alloys, there is a composition point, a function of these alloys, where again the freezing temperature and the freezing temperature, finish temperatures are identical. We term this temperature the eutectic temperature. Note that the eutectic temperature is much lower than the freezing temperature of either of the parent metals, hence the term easy melting. Alloys of the eutectic analysis, so the eutectic analysis, have the same freezing and start finish temperature at a constant temperature, so no freezing range, but because they still have to lose latent heat, they do have the time delay, a freezing start time and a freezing finish time. Now the constant freezing temperature we term the solidus line. The start of freezing we call the liquidus line, and below the solidus line all the alloys will be solid. Now some alloys, those that we can heat treat, so particularly important to heat treatable aluminium alloys, have solid solubility. And this means that in the solid state, aluminium can absorb into its crystals solute alloying elements. You see the solvus lines. The solid solubility is where the solid state, the solvent atoms can migrate and be dissolved or absorbed into the crystal structures of the solvent metal. Remember, it is the cloud of electrons in the metallic bond that hold metals together, so individual atoms can migrate. Now, as the solvus temperature increases, the atoms expand, so the solvent atoms can absorb more solute atoms, so solid solubility increases with temperature. So if you look on the graph, the blue line slopes forward, increasing solubility with temperature. And this is just like sugar dissolving into warm water. If you have a glass of of sugar and cold water, the sugar be at the bottom. As we increase the temperature, the sugar dissolves in the water. And on the graph that you can see, the solvus temperature, as the temperature increases, it slopes forward. So aluminium metal A will be able to absorb more of metal B. The increase in temperature increases solid solubility, so the line slopes forward. And this line we term solvus line. Earlier on, we have seen how metal atoms solidify into face-centered cubes and then into crystal lattices. Now we need to understand exactly how the chemical analysis changes of the solidifying metal crystals. In the case of a cooling liquid of specific alloy of A and B, as soon as the temperature falls to the liquidus line, freezing starts. In a liquid, the alloy atoms of A and B mix and move freely, and as the liquid cannot be solid, this freezing liquid would be slushy in the liquid. Remember, solidifying atoms, cubes of aluminium in liquid. Now, this area will become solid, so as this cools down, it'll become solid and it'll follow the solidus line, and the analysis will be A and B. So if you look on the graph, you can see that the cooling liquid has quite a high concentration of element B in A, sorry, but as it solidifies, it will follow the solidus line. So the actual analysis that will be solidifying will follow the solidus line, where you can see the solid line. And if you drop down the dotted line, you will see the actual analysis that will be solidifying. So as we solidify, the analysis will slightly change. So in the example, when the liquid cools, the atoms come together, start a face-centered cube. The face-centered cube will grow in 3 dimensionals to start a crystal. And as that crystal starts to form, the analysis of that crystal will form the solidus line. So it'll follow the analysis of the dotted line. And what will happen, it'll form a fledgling crystal, which you can see that blue crucifix starting to form. So that will be the first part of metal that solidifies out. Now, as solidification starts with atoms forming a single cube, the nucleation will grow into a crystal, and that crystal will have the analysis of A and B. Now, as we carry on cooling, the colder metal will solidify and into the mushy zone. So the analysis will change from pure liquid that started the analysis, and the analysis of the solidifying crystal will become richer in the solute atoms B. You can see that it's changed now, and you can follow the solidus line, and you can see that we have moved to the right hand side. So if you drop to the bottom of the graph, you can see the original dotted line shows the first analysis that solidified. Now, as we're solidifying the liquid, we've dropped the temperature, so the analysis follows a solidus line, and the analysis is moving to right. Now, that means that there's a chemical change in the analysis, which will change the next bits of the crystal's result solidifying. So the crystal will actually core. So the crystal that will form will have an initial core of the higher temperature solidification, and as it solidifies, the analysis will change, and the outer layers of the crystal analysis will change. We call this coring. Now, as the temperature falls to, as the liquid cooling temperature falls to the solidus or eutectic temperature, that's the freezing temperature, all the solidification will be arrested until the latent heat is lost. Then all of the alloy will be solidified as a eutectic concentration of A and B. And the chemistry of the final solidifying metal will be that of the eutectic, as represented by the 2 horizontal lines, A and B. So the solidifying crystal will form around the prior solidified chord structure and will solidify as a laminar structure of alternative bands of A and B. So the fully solidified metal crystals will consist of multiple grains of different concentrations. So the crystals will actually have in the core the very first piece of liquid cooling. Then as they cool down, the analysis had followed the solidus line, so the analysis changes. And when the solidifying metal reaches the eutectic temperature, we have this laminar structure. So the cast structures are heterogeneous, with the chemistry of the grains changing from the inside out. I hope you've enjoyed this module. I hope you now understand how metals solidify and how the chemistry changes. Please see some further reading. Thank you. Thank you very much.